So, welcome to cima.science. Our mission, simple: to flatten the world. Across the millennium, human civilization has always been organized with this pyramidal governance structure, with most of the people at the bottom and the governance at the top, made up of a very few select individuals through whom everyone must go to achieve anything. Even to get from one side of the pyramid to the other, you have to go up and come back down. As a result of with the financial markets collapse of 2008, we saw that didn't work. We couldn't trust the people at the top anymore. We realized that structure wasn't serving the people, and we have the advent of blockchain that holds the promise of the peer-to-peer platform, the peer-to-peer transaction platform, where people can transact business or interact with one another without having to go through the top-level governance. Unfortunately, the only people who could operate it, except for cryptocurrency, for example, the power of the smart contract that is so potent a tool to be able to give people the power of self-determination and economic autonomy, can't be operated by people who don't have a very substantial level of technological training: engineers, computer scientists, mathematicians, not even lawyers. And even though it's called a contract, lawyers themselves can't operate these things. So consequently, what we have is this tremendously promising technology of blockchain, decentralized consensus protocols, supposed to serve the people at the bottom, is serving only the people at the top. I've heard people tell me, well, blockchain's a game changer. I said, what's the game changer? Well, it reduces the cost for banks. How ironic. I have nothing against cost reduction for banks. I'm a free marketeer. We believe in the free market forces and economics. However, and if the banks, of course, pass along those savings to the consumer, all the better. Even if they don't, nothing wrong with profit, except that that's not what it was designed to do. It was designed to help the people at the bottom. So our goal, our mission at cima.science, is to flatten the structure to a pancake. And that is the mission for which I have founded cima.science. A work in progress for many, many years. Essentially, a project embodying my mission that I embarked upon a mere 43 years ago in the 1980s, the reason I became a lawyer in the first place. And now a project active in the last 5 years, and in the last 3 years in collaboration with Professor Serge Ladme, and now taking on its real shape. At cima.science, our goal is to take the disparate technologies, integrate the horizontal integration of technologies to create the tools that will facilitate transactions in a peer-to-peer platform with or without the use of an intermediary. Alongside that, we want to be able to bring that power of that technology to anyone, anywhere, anytime, anywhere in the world who wants to have the opportunity to do so. We are also designing and developing a vertical integration for technologies assimilator, which is simply metaphor for a spring delivery system, a vertical integration of technologies that will interoperably, but only optionally, serve to be able to deliver the technology of the peer-to-peer transaction platform to anyone who wants to have the benefit of it. We see it as a natural progression in the evolution of society, the natural evolution of society and technology that was actually begun much longer than us. We have here the mainframe computer, once operated using Fortran, and then only the top computer scientists and very few people in the world can operate this. And in this evolution, we have the Steve Jobs of Apple deliver the power of all that into a tiny little desktop computer. Imagine that. That was absolutely brilliant and an amazing feat to be able to take that and bring the power of computing right onto the desktops of people, something unimaginable prior to Apple Computer. But that actually started, that trend actually has antecedents long before that. 800 years ago, the man named Fibonacci, who actually discovered a technology, a tool in his day that reduced the friction of commerce to the merchants of his time, or actually the next couple of years. The rate of assimilation of technology at that time was certainly not the rate that we have today. He discovered Hindu-Arabic arithmetic. And prior to that, the way the computations were calculated by merchants was to go to a scribe. Your version, the equivalent of a comptable. A merchant could not calculate his accounts with another merchant or with a consumer, whomever he had interactions with, unless he first went to a scribe and determined what the accounts were. That was an enormous friction on commerce that actually was suffocating. It was operated in the way we think of as a tax today, that actually has served as an economic suffocation of economic activity and growth. So he writes the Liber Abaci that starts to disseminate the power of Hindu-Arabic arithmetic throughout Europe. And lo and behold, we have economic explosion of economic activity throughout Europe, merchants, trade routes opening up that ultimately created the economic wealth, the power, that ultimately financed some great things in history, including the sailing from Europe to the United States, and it was not then the United States, it was America, just the North American continent. And prior to that, around the same time, as a historical accident perhaps, we also start to have the first representation of decentralization of legal systems, where the King of England finally had to cede some part of his complete power that he enjoyed prior to that to what was then still only an oligarchy, but it was still a larger circle than his own single absolute power. These were the predecessors and the antecedents to the things that ultimately then gave way and gave shape to the Enlightenment, the Renaissance, and much of the thinking and much of the economic activity that we know of today that has actually fueled our modern society. Not too long after that, we had John Harrison solve the longitude problem to permit worldwide navigation by using nothing more than the string. He was a carpenter from England. And the King of England had given a huge prize to anyone who could solve the longitude problem. Why? Because he was losing mariners and ships by the thousands or tens of thousands. And they had the sextant, but they couldn't determine what the position at sea was. They could determine latitude with the sextant, but they couldn't determine longitude. And something as simple as a spring that was devised by a John Harrison carpenter, overcoming even something that Sir Isaac Newton was not able to devise at that time, created something that is called the marine chronometer. So a navigator at sea could determine his position, to determine longitude. We propose to use that same idea of the spring to spring into action and deliver to people anywhere, anytime, to anyone in the world, anytime they want to, the power of the ability to enter into a transaction. These are the opportunities and solve what is known as the Great North-South Divide, the latitude problem. And that is, in a nutshell, essentially the objective that cima.science proposes to achieve. We will realize this mission as a team of brilliance, led by the power of imagination, the courage to fail, with the perseverance to succeed. Talk to us. And on that note, I'd like to introduce to you the esteemed Professor Serge Vadnais, who will present the more technical aspects of this project. Thank you.
Okay, so thank you very much. So I guess that some of you can't wait for tomorrow to have my course. I will start today. Here the presentation is a bit more technical. I will try to enter into more details about what we are doing right now, and then you can imagine what will be the future. So first, again, so our objective is to bring the smart contract technology to people, and to every people, not only for the rich. So to keep in mind in this journey, so we have to think about inclusion. So we want to include everyone, and not only to develop something to help rich people to get richer. We want to include also people who don't have the education of people or students of the EPFL. So we want the tools we develop to be usable by our grandmas, for instance. We want to have the system to be deployable at scale, at a very large scale. We want it to be very secure. We want also not to rely on a single technology. So for instance, we will build on top of a blockchain, but if we want to switch to another blockchain, we should be able to do so very easily. So we need agility and also resilience. So if there is something which gets broken, can happen, unfortunately, we should be able to fix, to repair the broken piece and to restart easily. So that's a resilience. So what is our current roadmap? So just to summarize, so this is just a picture of what we envision. So we start working on smart contracts, and today we talk about the fair exchange problem. With a smart contract which is built on a blockchain, one problem is the gas price, the fees that we have to pay to make the contract run. So the gas price is a problem. The problem also of offloading. So if we want to have a very complex contract and to be able to run it, we have to make it run outside of the blockchain. And outside of the blockchain, we still need to keep the security of the blockchain. The blockchain keeps the evolution of the contract immutable, and we don't want to lose this property. These smart contracts, these are very complicated things, so we want them to be usable by everyone. So it means that we need to work quite a lot on the user interface. We want to have a good user experience. So it has to work for be ergonomic, easy to use, and also to include everyone, not only high-tech people. At some point, we will have to deal with identity systems, the identity management. So far, right now, so we can just imagine that an identity is just a public key on the blockchain. So anyone who has a registered public key on the blockchain can use it as his identity. But maybe we will want to have some more complex notion of identity, like for instance, use my own civil identity as a Salvadorese citizen of Switzerland, and I want to be able to do some transaction on this identity, not only on public key, which is registered on the blockchain. So we have to work with identity management. In some systems, we will also have to integrate some reputation mechanism. Because when people encounter to do some transaction, when they encounter at the very first time they don't know each other, they should have a way to figure out if they can trust the person. There is a problem of civil resistance with identity systems, like the problem of people creating many identities to do some bad things. So we have to protect against civil attacks in some cases, not for all applications, but some applications need some civil resistance. We need also a way to recover if we lose our keys, so we need some way to recover by using our own identities. Reverse mask, we want to talk about this. So we want to be able to encode any contract in a naive sense, any contract that we can write down right now. So we want to be able to encode it in the form of a smart contract, okay? So that it can be executed, and that it will be undeniable that we follow the terms of the contract by some ways of reverse mathematics. Maybe in the future we will also create a new blockchain so to take care to lower even more the gas price. So we'll have also to consider for this blockchain scalability, if you will be able to deal with many transactions and not only with a few for demo purposes, and also take care about the latency. So right now it's popular blockchains, you need to wait a few minutes to be sure that your transaction has been recorded on the blockchain. Maybe a few minutes, maybe too long. So we want to reduce that. And we also want to work on the hardware to use all this. So we won't necessarily rely on a smartphone or computers, but maybe develop our own hardware and think about the energy consumption, because we want this hardware to be usable at places where energy is not trivial to obtain, and also to consider the security against companies, adversaries, etc. After that, I have a few slides to detail all this, but I'm going to skip them. Okay. And I will jump to the problem of fair exchange to explain a bit more what it is about. So first, what is the problem in fair exchange? Imagine an exchange where you have two participants, Alice and Bob. Alice has some good X, Bob has some good Y, and they want to exchange them. So Alice wants to give X to Bob, and Bob wants to give Y to Alice. So Alice proposes this exchange, and then Bob says, okay, so he agrees to this exchange. So, and then Alice can send her good X to Bob. Bob can reply with his good Y, and then Alice signs, and they're both happy. So that's how an exchange should happen. So if Alice and Bob are in the same room and they do the exchange, it's hard to imagine that something bad will happen. So if, for instance, what could happen here is that when Bob receives the good from X, he could decide to take X and run. Okay? But if they are at the same place, maybe Alice can run after him. Okay? And maybe they can, it's one case of a dispute, but they have a physical way to resolve this dispute. Okay? Now, if the transaction is electronic, maybe Alice is in Switzerland, Bob is in another continent, they want to do this exchange. So how can Alice go after Bob, who is in another continent? There is no guarantee it will ever work. So we have to fix this problem, and it can be even worse. Bob could still be honest. Maybe Bob could have sent the good Y to Alice, but the delivery was blocked for some reason, which may be malicious reason. And Alice still didn't get Y. So the purpose of the fair exchange is to solve these problems and to make the exchange between X and Y somehow atomic, an atomic exchange, that you cannot break the exchange. Either the exchange happens or it is cancelled. So that's the problem of fair exchange. So we want to make this exchange atomic, and the problem of fair exchange has been a very long-lasting research question in computer science. It has many applications in many domains, like for instance, the problem of fair contract signing. So imagine that Alice and Bob want to sign a contract, so they both want to sign a contract, but they don't want to end up in a state where the contract is signed by only one person, because this person can be framed for having signed the contract. Now, if they're signed by both participants, they cannot be framed because both signatures appear in the contract. So that's the problem of fair contract signing. Another problem is the problem of fair payment. So that's the problem that we'll talk about in the next few slides. You want to exchange some good against some payment, and you want this exchange to be fair. Another problem, which is very similar, is the problem of certified email. You want to have an email delivery service in which the delivery of an email is in exchange of a receipt, of a signed receipt for reception of the email. So that's a certified delivery problem. You don't want to deliver the email without getting a receipt, and you don't want that the receiver gives a receipt without receiving the email. So that's also a problem of fairness. You can also imagine some other problem of fair exchange of secrets. Okay, so it has been a very long-lasting problem, and even in 1980, so we found a paper which essentially said that fair exchange is impossible to solve. Now this impossibility result has to be understood. So it means that if you have two devices, two processes, Alice and Bob, in isolation of all the rest of the world, we cannot design any protocol which will solve the fair exchange problem in a meaningful manner. So it means that we need to rely on some external services. So Alice and Bob together cannot solve the problem. So we need some external service, for example, a trusted third party. So this was understood as we cannot solve fair exchange without a trusted third party. If we do have a trusted third party, then the problem becomes trivial. So essentially, Alice sends X to the trusted third party, Bob sends Y to the trusted third party. When the trusted third party has got X and Y, can decide to send Y to Alice and X to Bob. The problem is trivial to solve. There is no way to make the termination unfair. So maybe the trusted third party can decide to abort if they don't receive both X and Y, and to send back what they have received. Okay, so that's if we have a trusted third party. After that, people started to make some fair exchange protocol where the usage of a trusted third party was kind of minimal. So they say, okay, so we will do an exchange between Alice and Bob, and if everything is honest, normally we don't need a trusted third party, but if we end up in a dispute case, we will involve a trusted third party who will help to resolve the dispute. That's the idea of the optimistic fair exchange. It's called optimistic in the sense that normally we don't use the trusted third party in normal cases, but we can use it if we need. So we do have a trusted third party, but in normal cases it's not involved. In some literature it's also sometimes called offline fair exchange, where the trusted third party is offline, and when we need a trusted third party, we call the trusted third party, and we help to resolve the dispute. So here is an example of a protocol. So that's it solves the problem of fair certified email with it's an optimistic protocol with a trusted third party who is here. So we can look at how it works. So imagine that Alice wants to send a message M to Bob. So she wants to send M to Bob in exchange of a receipt. So what she does is that she encrypts the message with some random number and with a key which is only known by the trusted third party. So she encrypts with the public key of the trusted third party, and only the trusted third party can decrypt. So she sends this encrypted email to Bob. So Bob doesn't know how to decrypt it, but you should know that the trusted third party normally would be able to decrypt it. So then Bob signs this encrypted email and returns a signature, and this signature plays the role of a receipt. Okay? So if this signature verifies, Alice is happy because she has got a receipt, but now she has to deliver the message in clear that Bob will verify that this message encrypts to what he received, and it corresponds to what he signs that he has received. Okay? So he didn't receive it here, he received it there, but he signed before that he received it. So what can go wrong is that Alice can decide not to send the message. So if Alice decides not to send the message, then Bob is annoyed because he has sent a receipt without receiving the message. So in that case, he can send this Z together with the signature that he has sent to the trusted third party. So he wakes up the trusted third party to resolve the dispute. And this trusted third party will verify that the signature, that the receipt is correct. And if it is correct, the trusted third party will decrypt Z and send the message to Bob and the signature to Alice, because maybe Bob may have claimed that he has sent the signature, but maybe he signed it, but he didn't send the signature to Alice. So here, at the end, the trusted third party sends the message to Bob and the signature to Alice, and it resolves the dispute. Okay, that's a very simple protocol, which is optimistic. It solves only the certified email problem, but we can do more. So actually, there was a protocol published before. It is a bit complicated, so we won't go through this protocol. And here, this protocol is only the optimistic part. The optimistic part between Alice and Bob. And you see that you have here several options. So if this step doesn't verify, then we have to run the procedure abort, which will involve the trusted third party. If this doesn't verify here, we have to run the procedure A resolve, which involves also the trusted third party. And here, if it doesn't verify, we have yet another procedure. So it's a complicated protocol, and it's a protocol to exchange signature. It's used for contract signing. So here, Alice has a signature on some document, Bob has a signature, and they want to exchange it in a fair way. Okay? The protocol is a bit complicated. Another protocol which is quite interesting so it's not an optimistic protocol, but here it's interesting because the trusted third party who is in the middle here does some computation which doesn't need to be secret, and that's actually the case of what is happening with the smart contract, except that it's this trusted third party should not reveal immediately what he received at this point. You can disclose it later, but the computation which is done by this trusted third party doesn't involve any secret. So that's very nice. And also, this trusted third party can be what we call honest custodians. So it's a threat model where the adversary follows the protocol, but he wants also to see some private information. And in that case, the trusted third party doesn't see what is exchanged between Alice and Bob. So he's involved, but he doesn't see what is exchanged. So that's also privacy, it solves the privacy problem. So that's an interesting protocol, but what we do is a bit different from that. Okay, another impossibility result was published in 1999, and this impossibility result, it looks a bit weird, because now it doesn't say we run Alice and Bob in isolation like the previous one. So now it considers some Alice and Bob running in some environment, but it says essentially that if we can solve the fair exchange problem, then we can solve the consensus problem, which is another problem in literature. So maybe you have seen this in some classes of distributed systems. So consensus problem is something which is also hard to solve. Protocol solving the consensus are very complicated. And there is a paper which says, which is giving what we call the FLP theorem, which says that the consensus problem is impossible to solve. So we may wonder, so what does it mean? It's impossible to solve because we know that consensus is used in blockchain. It's used every day by many people. So it means that it's impossible to solve if we assume no synchronization between participants and that the participants are deterministic. But normally, in the consensus protocol, we'll use a protocol which is non-deterministic and maybe which is synchronous, which assumes that the participants have a notion of epoch and they are synchronized with the notion of epoch. Okay? So we can solve in practice the consensus problem. So we may wonder, so is the consensus helping in solving the fair exchange? And the answer is yes. If we have a consensus, we have blockchain. If we have a blockchain, we have a smart contract. And with a smart contract can be a trusted third party. except that the smart contract is something which is public computation, so everyone can see. So the protocol we have seen before, we cannot use them directly. And yes, so that's essentially the problem of having a protocol which is based on fair exchange. So this is the definition of consensus and formalism. So I will show this protocol which explains how to solve the fair exchange with a smart contract. So now imagine that Alice wants to exchange X against payment of Y dollar. Okay. And X is characterized by a description function. So you have a description function of X which should be equal to D. So Bob say, I want to pay Y dollar against something which will satisfy this predicate. Okay, so that's a kind of contract. So if they agree on this contract, so Bob can pay a contract, a smart contract, and say, I want something which corresponds to description D. Okay? And now Alice will see that a smart contract was established with the right payment that she wants and the right description which corresponds to what she wants to sell. And then she can give X to the smart contract. The smart contract can verify if the description is correct. If the description is correct, the smart contract relieves the payment made by Bob and gives it to Alice. Okay, so that's what smart contracts can do. At the same time, since all the operation is done publicly, then Bob can see the X and essentially get the money. Okay. If what is submitted here is not X, then, okay, so Bob will see it, but the payment will not be released to Alice. And after some time out, the payment returns to Bob. So Bob didn't spend anything. Okay. So that's the idea of how to solve a fair exchange using a smart contract. One problem is that the smart contracts are expensive. If we deploy a smart contract in the blockchain, we have to pay some fees corresponding to the size of the code of the smart contract and to also the complexity of executing the smart contract, so the number of instructions. So we have to pay some fees. And this description function can be quite complicated. So we have to pay for the complexity of the description and also for the program to execute. So we want to reduce the cost. Okay? So here is a protocol which exists. I think it was implemented in a Bitcoin blockchain. It's called ZKCP, Zero Knowledge Contingent Payment. In this protocol, so Alice is essentially selecting an encryption key K, and she encrypts X, and she also hashes this encryption key to have some hash H. H could be revealed, but the property of the hash function is that from this description H, you cannot go back to the value K. Okay? So it's okay to disclose the value of H. Then Alice can release the hash of the key, the encrypted X, and she also gives a zero knowledge proof that she knows some X and keys, which verifies this equation. So this is not done using a smart contract. So she proves that whatever key which corresponds to this hash would decrypt C to what Bob is looking for. Okay? So now Bob is convinced that if he pays Y against a key which hashes onto H, he will be happy. So they set up a smart contract where Bob pays Y dollars, and he also says you can release the payment to whoever gives a pre-image of H by the hash function capital H. Then Alice sees that the contract was established, and then she can give the key to the contract. The contract will verify this equation, and if it is satisfied, the payment will be released to Alice. If it's not, nothing happens. And after a timeout, the payment is returned to Bob. Okay? And Bob can see the value of K arriving on the smart contract, and he gets the key. If it is correct, he can decrypt C and get X. Okay? And this smart contract is very elementary. It is what is called a hash time-locked contract, HTLC. It's available in many blockchains. It's very simple smart contract. Okay, problem with this protocol is that this zero knowledge proof is very complicated. Okay? It requires lots of computation for Alice to make this proof and for Bob to verify this proof. So we want to have something simpler, and there was a protocol proposed by Zemkowski in 2018, which is called a fair swap, where here Alice doesn't prove anything. She sends H and C to Bob, and Bob will say, okay, so I'm paying to the smart contract, I want a pre-image of H, and I also commit to the description I'm looking for. Then Alice will send the key to the smart contract, but the contract doesn't release the payment immediately. So Bob will first check if the key corresponds to what he's looking for. So he will get the key, he will check if it corresponds to the pre-image of H, like what was announced by Alice. If it decrypts C to some value X, which has a description equal to D, if it is the case, he's happy and he tells the smart contract that he's happy, so that the smart contract will release the payment to Alice. If he's not happy, then he has to say, no, I'm not happy with this key is not correct, and I can prove that this key is not correct by making a proof. So now Bob is making a proof only in the case of a dispute, but the proof is complicated, and the smart contract has to verify it. Maybe it is less complicated because it doesn't need to be zero knowledge. Now everything is open. Okay? So you can open all the values, give to the smart contract and say, you can verify, it doesn't decrypt to something that which corresponds to as a description. Okay, so we still have a problem, and this protocol was improved 2 years later, in 2020, by having another protocol where you have a dispute protocol. So here, the dispute protocol is essentially non-interactive. So Bob is making a proof that Alice did something bad, the contract verifies, and then the dispute is resolved. But you can have also an interactive way to resolve the dispute, like Bob sends a challenge to Alice, Alice answers, etc., etc. And it makes the dispute resolution simpler in the case of this protocol OptiSwap. So what we do is inspired from this OptiSwap protocol. So we do a bit more. So our protocol looks like this. When Alice wants to sell X against a payment of Y, what she does is that first she built a circuit corresponding to the description. She encrypts X with a key K to obtain a ciphertext, and then she commits to the hash of the circuit and the hash of the ciphertext to obtain a commitment. She sends a commitment to Bob, and Bob can verify that Alice committed to the right thing. So here the X is encrypted, so Bob doesn't see X, but Bob can verify that he committed to the right circuit corresponding to the description and the right ciphertext which was received. After that, Bob will set up the smart contract by saying that I received the commitment C, and here is my payment. And then the contract waits for a key to arrive. Alice will submit a key, and then Bob will have to verify if the key corresponds to what he's looking for. And if it doesn't, he says, no, this is a dispute. K doesn't correspond to the key which is making sense. And after that, we will have to prove to the smart contract that this is wrong, and without making a very complicated proof. So I did not explain the dispute resolution, but it is a very simple protocol. So this is a protocol that we designed, and we did a bit more. We also introduced the notion of sponsor to remove all the fees which are paid by the smart contract. Okay, so we have a protocol which can do some fair exchange for item which has an automatically verifiable description against a payment in cryptocurrency. So it's really a very special case. So in practice, we want to do other types of exchange. So we want, for instance, to exchange an item which doesn't have necessarily a verifiable description function against a payment which is in Swiss franc. Okay? Swiss franc is not a cryptocurrency. So So the problem is how to do it, so it will be the next step, how to design a protocol to solve this problem. So far we rely on a smart contract and we succeeded to minimize the cost, so now we have to implement. So we have other types of items to exchange. So here, so simple item, it's a digital item which is characterized by this description function. But we have some more complex, like for instance, if you want to buy a movie, it's still a digital item, but we don't have description function which will verify that it is the right movie we are looking for. Okay? So if we want to buy a movie, we don't characterize it by a function saying that this file corresponds to the movie I'm looking for. So the point is how to implement it. What else? So we may also be able to exchange some physical goods. So for instance, the fisherman, he wants to exchange a fish against a payment. So we don't have a function which verifies that what we have corresponds to our notion of a fish. And that's it. So next step would be to implement, to work on the user interface to make this usable by anyone. Then to have the fair exchange without cryptocurrencies and fair exchange with physical items, and also try to see can we use this to have a more general way to run a smart contract without paying too much fees, depending on the complexity of the contract. So, and for that, we need you to join and make it happen. Thank you.
Thank you. Thank you, Professor. Any questions? No? We thank you very much for joining us and for giving us the opportunity to tell you about the project. We welcome anyone who wishes to consider becoming part of the team to come and talk to us. We are now hiring people to actually start the implementation of the protocol Professor described, and including user interface. And we will then, in the very near future, be expanding what is right now going to be a very small team, to expand that sometime in next year to have a full deployment after we develop a concept. So if this is a project that could excite you and you believe in the mission, we welcome anyone who wishes to talk to us about doing so. Or if others you know they might be interested in working on this mission with us, we welcome you. Thank you very much.